Here's a velocity time graph of an object which starts with a velocity of 3 meters per second and 6 seconds later has got a velocity of 9 meters per second. So obviously the object has been accelerating. But what we want to try and find out is the displacement of that object. And there's two methods to do it. The first method, we're going to work with the average velocity. So the average velocity of an object is easily found. It's the starting velocity plus the final velocity divided by 2. Starting velocity plus final velocity divided by 2. In this particular example, we have the starting velocity to be 3 plus 9 and divide it by 2, and we get an average velocity of 6 meters per second. Now, once we've found average velocity, to find the displacement, we do this. Displacement S equals the average velocity times the time. So in our example here, the displacement S is going to be equal to the average velocity, 6 meters per second, multiplied by the time of 6 seconds, which is going to give us a displacement of 36 meters. So that's the first method of working out the displacement, the average velocity method. Now, the second method is to work out the area of the velocity time graph. The area of a velocity time graph will give you the value of the displacement. This is the same motion starting at 3 meters per second, ending up at 9 meters per second. So all we have got to do is work out the area of that velocity time graph. It's not in a particularly good shape, so what we do is we divide it up into two shapes that we can find the area of. And the first one is going to be the rectangular shape, a rectangle which fits in here. To work out the area of that rectangle is its length times its breadth, so it's going to be 6 times 3, and 6 3s is going to give us a value of 18. And the top part is the triangular part, and the area of a triangle is going to be a half the base times the height. So in this case we're going to have 1/2 times the base, which is going to be 6 along, and times the height from here up to there is from 3 to 9 is 6, so it's going to be a height of 6. So the area of that velocity time graph is made up of a rectangular part, 18, plus the triangular part, which is also 18.5 times 6 times 6 is going to give us 18. So the total area is 36, and we can then change that to displacement. Displacement is 36 meters. So there's two ways of working out the displacement from a velocity time graph. This method here working out the area of the velocity time graph, and this method here working out the displacement using the equation displacement as the average velocity times the time. And you have to know what the average velocity is. It's u plus v divided by 2. Now let's take a look at this velocity time graph. We're not looking at any numbers this time, we're looking at it in terms of the parts of the variables we use, the u, the starting velocity, v, the final velocity, and t. Now from that velocity time graph we can work out first of all the acceleration, and the acceleration is given as a change in velocity, v minus u, put a bracket around that, divided by t. That's the acceleration equation. Now we can cross multiply to give us v minus u is equal to 80. Now we can take the u from this side of the equation and take over to the other side, and it becomes plus, and our equation then becomes v final velocity equals starting velocity plus at. And that's a very important kinematic equation, because if we know the acceleration, if we know how long it was accelerating for, and we know the starting velocity, then we can compute the final velocity of the object. So that's a very good kinematic equation. But what we'd like to know is there one for the displacement of the object? Well, from our previous examples, we know that the displacement of an object is equal to the average velocity times the time. And we know the average velocity is 1/2 of the starting velocity plus the final velocity multiplied by t. Now this v here we know is equal to that v there, which is equal to u plus at. So we can exchange this v for u plus at, and we get our displacement s will become 1/2 into u plus, and it will be u plus at multiplied by the t. Now inside the bracket we have got 2u, so we have displacement will be equal to 1/2, and we'll have inside the bracket 2u plus the at and multiply it by the t. And if we multiply through by the half and the t, we should get the following: half times 2 is 1, so 1u multiplied by the t is going to give us ut, plus a half times the a times the t times the t, it's going to give us 1/2 at squared. Now that's another important kinematic equation, because we can work out the displacement of the object if we know the initial velocity, we know its acceleration, and we know the time it took to accelerate. We can work out the displacement of that object. So that's us now got two kinematic equations. We have the v equals u plus at and the s equals ut plus 1/2 at squared. Now, would we get the same answer if we to work out the area of the velocity time graph? Well, let's see. The area of this velocity time graph we split up into two parts. There's our first part here, our rectangle part, and there is our second part, which is our triangle part. The area for the rectangular part is just tu, so it's ut, and the area for the triangle is 1/2 the base, which is t, times the height of the triangle, and the height of the triangle is going to be v take away u. So there we have the two areas. So the total displacement according to the area method will be equal to the rectangular part ut plus 1/2 t into v minus u. That doesn't really look very good, and there's nowhere, well, it's very close to that previous equation. It'd be really good if we could exchange the v minus u part and get rid of that and see what we would get. And we can do that because we know from a previous experience that v minus u is equal to the acceleration times the time. So we can swap over and have displacement s equals ut plus 1/2 t times at. And we can make that a little bit simpler by saying displacement s equals ut plus 1/2 t times t is t squared, and the a, and we say 1/2 a t squared. And that's the kinematic equation which we derived when we did the average velocity method. So that's a very important kinematic equation. The ut part is really the displacement caused when there's no acceleration, and the 1/2 a t squared part is displacement caused when we have an acceleration of a meters per second per second. Now, so far we have the following kinematic equations. We have got, well, we can put in the displacement s equal to 1/2 u plus v times t. And that comes from the fact that the displacement s equals the average velocity times the time. And we've also got v equals u plus a t. And we've also got displacement s equals ut plus 1/2 a t squared. Now notice every one of the kinematic equations so far has got time involved, and what we'd like to do is get an equation where there's no time involved. So let's see if we can try and arrange that. We'll start off with our very basic equation over here. We'll start off with v equals u plus at, and what we'll do is we will square both sides. So we'll have v squared equals bracket u plus a t all squared. So this gives us v squared equals, and we multiply out the brackets, first term squared, u squared, plus double the two terms multiplied together, so it's 2u a t, and plus this term squared, a squared t squared. Now that a squared t squared is very similar to our equation up here, ut plus a half at squared. And in this part we can see that it's hidden in there. We have a u, we have a t, ut, we have an a squared and a t squared. Well, we've got an a and a t squared there. So to make this simpler, we could do the following: v squared equals u squared plus, and we're going to take out a common factor of 2, and we're also going to take out a common factor of the acceleration, because that appears there and there as well. We'll just leave the t in. So 2a into a bracket is going to give us ut. That's what we're looking for. Plus, because we've taken out a common factor of 2, we have to have a half in here. And because we've taken out an a, one of the powers has got to be reduced. We're going to have at squared. Now, we can see that ut plus a half at squared, this whole bracket here, is in fact equal to displacement s. S equals ut plus a half at squared. So what we can do now then is we can change all this bottom line to give us v squared equals u squared plus 2 times acceleration, and this bracket here becomes the displacement s. So there's our kind of fourth kinematic equation. We've got 1, we've got 2, we've got 3, and we've got another one, and we can put down that as v squared equals u squared plus 2 times acceleration times s. Now the beauty of this equation is that it's not got time involved in it. If we know the final velocity, if we know the starting velocity, if we know the acceleration, then we can work out the displacement of that object. So there's our key kinematic equations. Average velocity times the time is displacement. V equals u plus at. S equals ut plus a half at squared. And finally this one here, which has got no time involved in it, v squared equals u squared plus 2as. These are the kinematic equations.
Physics is wonderful. Physics is cool.